Welcome to the Deep Dive, where we take the densest source material, the articles, the research, those high-level concepts, and really try to distill the core insights you need. Today, we're tackling a huge one, a really foundational question that sits under, well, all of modern technology and philosophy. Is the human mind a computer?
Yeah, this is pretty much the ultimate question for anyone interested in artificial intelligence. And, the simple answer is often tempting.
Right.
But the true deep dive requires rigor. So our mission here is to first define really precisely what a computer is, using the language of theoretical computer science. Then, and only then, can we properly analyze that philosophical theory called computationalism. The idea that your mind is, basically software running on your brain's hardware.
Okay, let's unpack this. This is a crucial journey because we can't just define the mind from our modern perspective. We have to trace the whole argument. We'll start with the intuitive, kind of old-school understanding of consciousness, trace the conceptual detour that gives us the definition of computation we need, and then throw that definition up against the biggest philosophical challenges. And we'll land on the cutting edge of modern AI architecture. So let's get started. So where do we begin? I guess we have to start with the philosophical default, what our sources call the pre-theoretic intuition. Dualism. Why did thinkers like Descartes feel so certain that the mind and body were, fundamentally separate substances?
Well, it really just comes down to basic personal experience. There are two big arguments for this separation. The first is what's called the argument from introspective appearance. When you close your eyes and you think about your mental life, maybe you're recalling the smell of, fresh coffee, that subjective experience, it doesn't feel like a cascade of electrochemical discharges in your neurons.
I get that. I have, unique, privileged, direct access to the feeling of thinking about chocolate ice cream. No one else can get inside my head and access that exact sensation. It's totally different from a physical object, which anyone can look at.
Exactly. And the second argument is from essential properties. Physical things, like a chair or a planet, are essentially spatially extended. They take up space, they have dimensions. The mind, though, it seems to be essentially a thinking thing, something that doubts, desires, believes, and it just doesn't seem to be spatially extended in the same way. So the dualists concluded they must be different kinds of things.
But that dualistic separation, it creates this almost impossible problem. How do the two things, this immaterial mind and the physical body, how do they even interact? So the philosophical community eventually pivoted, leaning into materialism.
Yes. Specifically, theories like what was called Australian materialism, which made a very bold claim that mental state types are identical to neural state types.
So my sensation of pain is literally the same thing as a specific identifiable pattern of C-fiber firing in my nervous system.
That was the idea. But this is where the theory just hits a concrete, fatal wall, a concept called multiple realizability. And this is foundational to our whole deep dive today.
So tell us what it means and why it just completely killed that classical materialism.
The problem is one of variety. Look, if desiring ice cream were identical to a single type of neural firing pattern, let's call it pattern N7, then only a system that has N7 could feel that desire.
Okay.
But we know mental states are more robust than that. Your desire for ice cream is realized in your brain, which is unique. My desire is in my brain. A dog might realize a desire for a treat in a totally different neural structure.
And critically, a future AI could have a desire for, data processing, and that would be realized in silicon hardware.
Precisely. If different physical materials, different biological substrates, different types of wetware or metalware can all support the same mental state, then that mental state can't be identical to any single physical state. That one-to-one link is just broken.
So the substance doesn't matter. Only the functional relationship matters. And this brings us to functionalism, which is really the bridge to computation. Functionalism says a mental state is defined not by what it's made of, but by its causal role.
The classic analogy is a mousetrap. You can build a mousetrap out of wood, metal, plastic, whatever. What makes it a mousetrap is its function, its causal role in mediating a stimulus, like a mouse, to a behavior, snapping shut. Mental states, in this view, are just defined by how they mediate sensory input, behavioral output, and transitions to other internal mental states.
And this is the moment everything changes. Because if the mind is defined by its function and not its substance, it promotes what our sources call substrate independence. The mind could, in theory, be instantiated in wetware, metal, anything, as long as it performs the right computations.
Okay, so if the mind is functional, and functionality means mediating states, we have to ask, what's the most rigorous way to define a system that mediates states based on roles? And the answer is the formal system. This is the definition of calculation itself.
Right, this is where we get super specific. So what are the two essential components of a formal system?
A formal system needs two things. First, a collection of effectively distinguishable states. Think of the squares on a chessboard. You have to be able to tell them apart mechanically. Second, it needs a collection of rules that operate effectively on those states to generate new states.
Let's focus on that term, effectivity. It sounds technical, but it's so critical because it dictates the absolute limits of computation. What does it mean for a procedure to be effective or algorithmic?
An effective procedure is just a set of steps, an algorithm that can be completed in a finite time by just following the steps without needing to understand the meaning of the task. It's totally mechanical.
Like a recipe. A chef doesn't need to understand the chemistry, they just follow the steps.
Exactly. So distinguishing chess states is effective because the rules are finite, the board is finite. You can check the state in a finite number of steps. Now contrast that with, say, trying to count all the natural numbers. The process is defined, but it is not effective because it goes on forever. You can't complete it. The power of computation lies only in procedures that are effective.
What's fascinating here is the sheer power of formality. If the operations are purely syntactic, based only on shape and rule, not meaning course, then the system's operations are totally independent of the medium.
That independence is called isomorphism. If you and I are both playing chess, one of us with wooden pieces, the other with symbols on a screen, we are playing the exact same formal system. The underlying rules are structurally identical, or isomorphic.
And to make this concrete, mathematicians and computer scientists define the limits of computation using concepts like register machines.
Right. Register machines are these abstract formal systems that use numbered registers, or storage spots, and they perform only the simplest operations. Increment, which is add one, and decrement, subtract one. And even with just those basic instructions, these machines can compute almost any function we can write an algorithm for. But they also revealed a fundamental limit, the halting problem.
The halting problem. One of those big takeaways from theoretical math, showing there are certain questions computers, by their very nature, can never answer.
Precisely. The halting problem proves there is no single effective procedure, no algorithm that can look at any random program you give it and determine in a finite time whether or not that program will ever stop running. It's an undecidable question.
Wait, so if the human mind is a computer, doesn't that imply that our minds are also subject to the halting problem? Are there, like, fundamental truths or problems that we, as effective systems, can never solve?
It is a huge philosophical consequence, yes. It puts a hard boundary on pure algorithmic reason. But let's get back to the machine. To get from a simple register machine to a modern computer, you need one final piece, the universal machine. And this requires a genius trick called Gödel coding.
The trick where we turn an entire program into a single number.
Exactly. Gödel showed how to assign a unique effective code, a single natural number, using prime exponents to represent any formal system or program. And what's critical is that this means a program can be treated as input data for another program.
So we can code up the instructions for register machine alpha and just feed that code into register machine beta.
And if beta is designed correctly, it can read alpha's code and execute its instructions, effectively simulating alpha. This single program, this register machine beta that can simulate any other program, is the universal machine.
And the existence of a universal machine proves the case for substrate independence. It shows that any computation can be run on a single general-purpose piece of hardware. This is the theoretical basis of the modern computer and, of course, the foundation of computationalism. So with the universal machine established, the computationalist claim comes into really sharp focus. The human mind is an isomorphism of a single, very complex formal system, which we'll just call mind. Our mind is software, our brain is hardware.
And this framework is actually very powerful for explaining complexity and variation. For example, why do two people react differently to the same stimulus? Well, computationalism accounts for this by saying both people may run the same underlying software, mind, but they're just in different states at that moment.
Different states, meaning different values are assigned to their internal variables, their beliefs, their memories, their desires. It's just like two computers running the same OS can have different data in their registers.
Precisely. The system is the same. The momentary states differ. So if a machine can run this formal system, how do we test for genuine mentality? That brings us to the most famous behavioral test, the Turing test.
Proposed by Alan Turing back in 1950, it suggests that if a machine can convince a human interrogator that it is human through conversation, then we have strong grounds to attribute a mind to it. It's a linguistic barometer for intelligence.
And Turing was famously optimistic. He predicted that by the year 2000, machines would be convincingly passing a test of moderate duration.
Yeah, that optimism proved a little misplaced. Our sources reference things like the Loebner Prize, these long-running Turing test competitions, and they show that even today, after decades of advancement, it often only takes a simple, pointed line of questioning to tell the machine from the human.
Right. And the failure of the Turing test to be reliably passed led philosophers to ask a crucial question. If a system can process language inputs and spit out appropriate language outputs, but it still isn't convincing, what is it missing? What does that language processing lack if it doesn't lead to genuine intelligence?
This brings us to the really hard problems that computational functionalism just struggles to answer. The first great objection challenges whether computation is sufficient to generate meaning. This is the Chinese room argument.
This is a famous thought experiment from John Searle, and it's designed to attack the idea that purely syntactic manipulation, just following rules, is enough to generate semantics or, meaning.
So lay out the scenario for us.
Imagine you are locked in a room. Inside, you have this enormous instruction manual written in English. The room has a slot where slips of paper covered in mysterious symbols, let's say they're Chinese characters, are passed to you.
And you, the agent, you don't understand any Chinese.
Not a single word. You only follow the English rule book, which tells you things like, if you see character A followed by character B, then output character X followed by character Y. You're just matching shapes.
You're acting as the CPU of the machine.
Exactly. Based purely on the shape of the symbols, you manipulate them according to the formal system. Now, outside the room, native Chinese speakers are feeding in questions and receiving perfectly coherent, sensible answers. From their perspective, the room is passing a Chinese Turing test.
But, and this is the critical point, you, the human agent inside manipulating the symbols, you do not thereby understand Chinese. You are performing a computation, but you didn't acquire any meaning.
That is the knockout punch. The room, the program, it manipulates syntax perfectly, yet there is no grounding of meaning. The symbols in the room don't refer to anything for the agent inside. It seems meaning requires something more than just formal rule following.
Which would make computational functionalism, based only on syntax, incomplete.
Incomplete, yes.
And if semantics challenges the meaning of thought, the second great objection challenges the feeling of thought. We're talking about qualia.
Right. Qualia are those privileged, subjective qualities of experience. What it's like to taste coffee or what it's like to feel pain. The classic argument here is the Mary the Scientist thought experiment, also called the knowledge argument.
So Mary lives in a black and white room and studies the physical world. She knows all the physical facts about color, every detail of neurophysiology, light wavelengths, how the cones in our eyes fire. She knows everything that science can know.
But then, for the first time, Mary is allowed to step outside the room and she sees a red rose. And the argument asks, does she learn something new?
And the answer seems to be yes, she does. She learns what it is like to see red. So if she learned something new and she already knew all the physical facts, then that new knowledge, the qualia, it must be a non-physical fact. It's left out of the purely physical or functional accounts.
And this leads directly to the ultimate challenge, the philosophical zombie. We ask you to imagine an imitation man, a zombie, who is functionally identical to a human. He walks, he talks, he laughs, he flinches when you prick him with a pin. His brain processes input and produces output exactly like yours does.
But the key distinction is that he completely lacks qualia. His pain flinch is functionally perfect, but the pain state doesn't feel like anything to him.
And if this imitation man is possible, and philosophers argue he's at least logically conceivable, then function alone is not sufficient for mentality. To have a mind, you seem to need the function plus the subjective feeling. The hard problems we just talked about, particularly the Chinese room's attack on that rule-based symbolic approach, well, it led to a major shift in computer modeling in the 1980s. The rise of Connectionism.
And this is the architecture behind modern artificial neural networks, or ANNs. So instead of relying on symbolic rules like if A, then B, Connectionism models information processing using what's called parallel distributed processing. What does that architecture even look like?
It's a huge move away from the single CPU model. ANNs use a vast number of simple processing units, or nodes, all operating at the same time, in parallel, much like real neurons. Information is distributed across the whole network, not held in discrete symbols, and processing happens through the propagation of activation across weighted connections.
And those weights are crucial, aren't they? They determine the influence one node has on another.
Yes. Connections can be excitatory, which is a positive weight that encourages the next node to fire, or inhibitory, a negative weight that suppresses it, a node only fires if the sum of its incoming activation hits a certain threshold. And learning happens by adjusting these weights over and over until the network produces the right output.
This architecture is amazing at tasks that traditional symbolic systems just failed at, especially where rules are messy or context-sensitive. The example from our sources is translating written English into spoken sounds. English is just not pronounced as it's written.
It's a perfect example. If we designed a network to figure out when to produce the S sound, a symbolic system would struggle because the rule has so many exceptions. A connectionist network just learns the context.
So it learns to inhibit the S sound when the letter S is followed by H, like in wish or shy, but it also learns to excite the S sound when it sees a C in contexts like ice. It learns these patterns statistically through training data.
Exactly. The real power here, the power of connectionism, is its innate capacity for pattern recognition. ANNs naturally extract and encode these incredibly complex, noisy patterns from training data. And this capacity is deeply implicated in human processes we associate with, intuition and analogical reasoning, which are often not very algorithmic and are super context dependent.
So we have symbolic AI, which is rule-based and discrete, and connectionism, which is pattern-based and statistical. Are they fundamentally opposed?
Well, our sources suggest they might not be rivals after all. It's actually pretty likely they're just different levels of description.
Yeah.
The high-level functions of human cognition might be best described symbolically. I believe X, I desire Y. But the underlying neurological implementation, the actual wetware that makes those beliefs happen, that might be best described by the subsymbolic parallel processes of connectionism. So our deep dive has really illuminated a crucial point. Computation, even in its most successful connectionist forms, is almost certainly necessary to explain mind-like behaviors and intelligence. But because of the problems of the Chinese room and qualia, it's unlikely to be sufficient. The mind requires more than just formal syntactic manipulation. It demands semantics and subjective experience.
So what does this analysis impose on the engineering of a truly conscious AI? I mean, we've established that to solve the problem of meaning, to develop genuine semantic representations, that system has to have embodied experience. It needs a body, a sensory apparatus that connects it to the external world, grounding its internal symbols in real-world consequences.
And that leads us to a final sort of provocative thought, one that connects this ancient philosophical debate with our modern technological ambitions. Given the requirement for complex, non-algorithmic function, the incredible intricacy of the brain's physical wetware, and the critical need for embodied experience to develop semantics, by far the simplest way known to science and philosophy to create something that is guaranteed to develop a mind in the human sense is still the old-fashioned biological way, to create and raise a human being.